Welcome to 24 Hours of PARS, Summit Preview 2015. We're excited you could join us today for Kalen Delaney's sessions, highlights from her PARS Summit Precon Index Internals, Rowstore, ColumnStore, and NoStore. This 24 Hours of PARS event consists of 24 consecutive live webcasts delivered by expert speakers from the PARS community. This session is a preview of one of the many technical sessions that will be presented at PARS Summit in October this year. Recordings may be available in 1 week at www.24hoursofpars.com. My name is Howard Diesel. I live in South Africa and love SQL Server. I have a few quick introduction slides before I hand over the reins to Kalen Delaney. She will speak for 40 to 45 minutes and then we'll move on to questions and answers where you can ask any question you may have. Next slide. If you have any questions or if you're experiencing any issues, just type your question into the question pane on the GoToWebinar control panel and someone will assist you. Feel free to enter your questions in the Q&A field at any time. Once we get to the Q&A portion of the session, I'll read off your questions to the speaker. Since all attendees are muted, you will need to submit questions by typing in the Q&A field. Also, there will be a short evaluation at the end of the session. Your feedback is important to us, so please take a moment to complete it and it will appear in your web browser. Next slide. "24 Hours of PARS would not be possible without the support and dedication of our sponsors. They are the reason this event is available to you free of charge. I'd like to take a moment to thank our presenting sponsors, Microsoft, Dell Software, and Idera. In addition, I'd also like to thank the supporting sponsors for this event, HB, SQL Sentry, and Pyramid Analytics. Next slide. Next, I'd like to bring to your attention the upcoming PARS Summit, taking place in Seattle, Washington, from October the 27th to the 30th. PARS Summit 2015 will feature over 200 sessions with world-class SQL Server experts. Planned and presented by a SQL Server community for the SQL Server community, PARS Summit is single-handedly the largest gathering of SQL Server and BI professionals in the world. With over 5,000 registrations from all over the world, PARS Summit is also a great place to network and meet face-to-face with experts, peers, and MVPs. More importantly, PARS Summit delivers on providing you with the answers to your SQL Server issues, along with the knowledge, strategies, and skills you need to stay ahead of the curve. Save $200 right now by using the discount code 24HOP15 when you register. Optimize your savings by registering before the end of Sunday, September the 20th. To find out more about PARS Summit, visit www.parsummit.com. Next slide. Make sure you explore everything PARS has to offer for data professionals. You can join local user groups around the world, virtual chapters, find free online resources through our Learning Center, and read up on the latest community news in the Connector newsletter. For those interested in business analytics, check out the PARS Business Analytics Conference happening in May next year. Visit www.parsbaconference.com for more information or to subscribe to our bi-weekly BA newsletter. Next slide. And now, please allow me to present the speaker of the hour, Kalen Delaney. Kalen Delaney is a SQL Server MVP who has worked with SQL Server for over 27 years. She has provided performance consulting services and taught advanced courses on SQL Server to thousands of people and organizations. In addition to her courseware development, Kalen has been writing about SQL Server for years. She is the primary author of SQL Server Internals and the Inside SQL Server series. Kalen is also one of the primary editors for Redgate SQL Server Stairway tutorials. Over to you, Kalen.
Well, thank you very much, Howard. And welcome, everybody. I don't think it hit me until we started preparation for this that it was middle of the night in much of the world. It's evening on the west coast of the U.S. where I am, but other people could be anywhere, anytime. So those of you joining us live, I very much appreciate your enthusiasm, and certainly those of you who will be listening to this on the recording probably have no less enthusiasm, but maybe a little more need for sleep. So welcome again, and I would like to tell you a little bit about what I will be covering in my Precon at the upcoming PASS Summit. I will be speaking for a whole day on indexes, but I'm going to tell you what I think are some of the most useful tidbits to know that we can get across just in our 45 minutes now. So there's another information slide about me, and the only thing I will call out here that Howard did not already mention is that my most recent book is one published by Redgate on the new in-memory technology introduced in SQL Server 2012. I'm sorry, introduced in 2014. So I do have a whole book about that called SQL Server Internals In-Memory OLTP that is available from Redgate. A PDF is available for free download, or it can be purchased also. So I'm not going to step through word for word the abstract that I have for my whole Precon, but I do want to just point out to you that indexes have always been one of the most important features of the product if you care at all about performance. So a news group that I participate in, actually someone just asked the question for everyone participating to list what they found as their most oft occurring performance issues. And the majority of people somewhere near the top of their list listed indexes, that having the wrong indexes or not having indexes at all, or possibly even having too many indexes can actually be one of the main performance inhibitors. So understanding what indexes are useful for and how to think about the best indexes for your tables, for your queries, can make an enormous difference in your overall application performance. There are three different kinds of indexes that I'm going to be talking about in this session now, three different kinds that I talk about in a lot of detail in the full day session. So the three kinds I'm referring to, as in the title of the session, the Rowstore Indexes, the ColumnStore Indexes, and the NoStore, and I'll tell you where that name NoStore comes from. And then I'll tell you a little bit about each of the three types of indexes, and then I'll also give you some comparisons about some of the operations that are done on indexes, some of the additional data that's kept for indexes, and how this varies between the three different types. So Rowstore is historically what we've always had. Prior to 2012, it was all that we had. Rowstore indexes are indexes that are stored on pages just like your data rows, and there are rows for the indexes. In fact, in a lot of ways, the index rows look very much like the data rows, so we call them Rowstore, index rows on pages. The pages are organized in a tree structure that we call a B tree, and we will have a graphic of a B tree on the next slide. B trees can be either clustered or non-clustered, and I will tell you a little bit about what the difference between them is. Each of the index pages can have multiple index rows on it. Usually it will have lots and lots of index rows, but it might just have a few. When or why it might just have a few is a little more than we can talk about in this short session now. In the index, as it's organized in a tree structure, rows on upper levels are slightly different than rows on lower levels. Rows on the upper levels will have pointers to pages lower down. Rows at the lowest level are considered leaf rows, and these are quite a bit different than the rows at the upper level, as I'll discuss on the next slide. So here's a picture of a B tree. The B in B tree stands for balanced, And what balanced means here is that it's always the same number of levels going from the root to the leaf. You can see a single page at the root level. That's part of the definition of root, is a single page. There may or may not be intermediate levels. In this diagram, I have one intermediate level, but we might have many. There might be 0. And then the lowest level is the leaf. And the balanced tree, the B tree term, refers to the fact that any point on the leaf, any page on the leaf, is at the same level down from the root. It's always 3 levels: root, intermediate, leaf in this particular example. Now, in both clustered and non-clustered B tree indexes, which is another name for the Rowstore that I'm talking about first, both clustered and non-clustered have a particular property, and that is at the leaf level, there is a row in the index for every single row of data. Now, the one exception is if you have filtered indexes, but we won't be talking about filtered indexes in this short session. There is one row in the leaf level for every row of data. So we could just count the leaf level rows, and that would give us a count of the number of data rows. Even if there's duplicates, there's a row in the leaf for every single duplicate value. The other property of the leaf level, besides having every single key value there, the key value is the value that the index is built on. Besides having every key value in the leaf level, they are in sorted order, and the sorting is relevant to whatever the data type is. If it's a character data type, they're sorted using whatever your collation is. If it's a numeric data type, they're sorted numerically. If it's a date-time data type, they're sorted chronologically. So every key value is there in order. But then the question that arises is, if both clustered and non-clustered have every single key value in order in the leaf level, what's the difference between clustered and non-clustered indexes? Well, that's on the next page. The difference between clustered and non-clustered is actually the answer to the question at the top of this slide. In fact, I could add another word to this title and say, what else is in the leaf level? What else besides every key value? The answer to what else is in the leaf level for a clustered Rowstore index is everything else. In a clustered index, the leaf level is the data. It is not a copy of the data. It is your data. So if you have a table with no clustered index, we call that a heap, by the way. If you have a table with no clustered index, and then you build a clustered index on it, SQL Server takes that data and just rearranges it. It sorts it in index order and then builds the upper index levels to point to that data. If you look at your query plans and you see an operator that says clustered index scan, you should know that's exactly the same thing as a table scan. I've overheard people look at plans and say, oh, good, it's using an index, it must be okay. If you think table scans are bad, and I'm not going to say they're not bad, but I'm also going to give you a sneak preview and say they're not the worst thing that can happen. But if you think table scans are bad, a clustered index scan is just as bad because it's exactly the same thing. It's looking at every single row on every single page of the table or every single row on every single page of the leaf level, which is the table. Another property of clustered indexes is that they must be unique. That doesn't mean you have to declare them as unique. It doesn't mean they have to be built on unique data. But if your data has duplicates, SQL Server will uniqueify them. What that means is anytime SQL Server sees a repeating value, it will add a hidden key. So if you have a clustered index on last name, the first Meyer won't have any duplicates, so it won't have this hidden key, but the second Meyer will have a 1, and the next Meyer will have a 2, and the next Meyer will have a 3. You'll never see these hidden values when you do a select or any other data access operation, but they are there. They are stored on the pages. So the clustered index leaf level is your data, and it is in index order. Non-clustered indexes are separate from the data. Non-clustered indexes, the leaf level contains every key value, but then there is a pointer, also called a bookmark, which actually indicates where in the actual table that row can be found. So if your clustered index was on last name and your non-clustered was on first name, the non-clustered on first name would have every single first name value followed by, in the index row, a pointer saying this is where in the table that row can be found. What do these pointers look like? Well, it depends. It depends on whether the table is a heap or whether the table has a clustered index. If the table is a heap, the pointer or bookmark is the actual address of the row. The file number, the page number, and the row number, which we also call the slot number. That three-part identifier is the row ID. If the table has a clustered index, however, so we can call that a clustered table, the pointer or bookmark is the actual clustered key value. So what would this look like? If your clustered index is on last name, the data is then organized with all the Adams and all the Bakers and all the Charlestons nice and neat and in order. The non-clustered index would be sorted by first name, Ann's and Bob's and Charlie's and Diane's. And for Anne, there would be her last name as her clustered index key. So it would say Anne's last name is Zuckerman and Bob's last name is Frankel, and Charlie's last name is Smith. But if there's lots of Smiths, the uniqueifier, this hidden key added to the clustered index, is part of the key, so it's also part of the pointer from the non-clustered. Charlie's last name is Smith 47 would be stored in the leaf level of the non-clustered index. So when should you use this kind of index? Well, it's basically the default choice. Again, this is the only kind of index that we had prior to SQL Server 2012, so you didn't have a choice to use one of the other two kinds of indexes. But even if you're going to be using a B-tree index, a Rowstore index, you still need to decide whether that index should be clustered or non-clustered. You only get one clustered index. The data can only be sorted in one order. So very frequently, the choice for where your clustered index should be put, what column the clustered index should be on, is what's the ideal sort order. If you're frequently sorting by last name, putting the clustered index on last name means that the data is already sorted and doesn't have to be sorted during query processing when you ask for it in a sorted order. Or if you're just looking for a range of last names, give me all the last names that start with a letter between G and M. They're all together, easily accessible in the clustered index. Or if you've got duplicates, if you want to know everybody in a particular postal code, a clustered index on postal code means all of the rows with that same postal code will be together. In those cases, you can consider a clustered index, whether for the data that has to be sorted, or the data that you're looking for a range, or the data that has a lot of duplicates and you want to find all the rows that have that same duplicated value. Non-clustered indexes, on the other hand, are typically only useful when you're accessing just a few rows. And I put few in quotes there because it's not an exact number. Some people will try to throw out a percentage number when it's more than this percentage, more than 10% of the rows in the table. But forget I said that. It's not 10%. It completely depends on the size of the rows, the size of the keys, and how many rows are going to meet the condition. What percentage of the table it's going to be is compared to the cost of using other options. So frequently it's maybe only 1 or 2% of the rows in the table. It might be as many as 5 or 10%, but SQL Server decides what index to use based on a costing formula, and if using a non-clustered index is determined to be the cheapest, it will be used. But it usually turns out that a non-clustered is only useful when you're looking up a few rows. The reason for this is because in the leaf level of the non-clustered, there's a pointer to somewhere in the table where the actual row can be found, and for each of those rows you're going to have to do a lookup into the table. You want to keep those lookups to a minimum. So looking for all of the rows where last name equals Zuckerman might just return a few rows, and a non-clustered on last name could be fine, but looking up all the rows where first name, I'm sorry, I was mentioning last name, wasn't I? Where last name equals Smith would be a whole lot of rows, and it may be that the non-clustered wouldn't be useful. One special case of non-clustered indexes is an index where you don't have to go to the table itself, where all you're interested in is the data in the index. If I have an index on first name, a non-clustered on first name, and I just want to know how many Josephs there are, every single Joseph is in the non-clustered index leaf level, and SQL Server doesn't have to go to the data at all. That's called a covering index. If you can build a covering index for a query, it's an excellent use of the non-clustered index structure. But in SQL 2012, Microsoft introduced a completely different way to store indexes, basically turning them 90 degrees. SQL Server 2012 introduced ColumnStore indexes. We store, instead of index rows, we store columns. We will have a graphic on the next slide, which hopefully will make this a little bit clearer. 2012 introduced non-clustered ColumnStore indexes, and then in 2014, Microsoft added clustered ColumnStore. I will tell you the difference between these shortly. For either kind of index, SQL Server takes all the rows and splits them into groups called row groups, and then each column in the index within each row group is stored as a segment. The number of rows in a row group has a fixed upper limit. It doesn't always have to reach that upper limit, but it can't go bigger than that. Each segment is stored as a single value. This will be clearer when we look at the picture on the next slide. SQL Server takes all of the values in one column in one row group, that is one segment, and crunches it together, uses a compression algorithm and an encoding, and stores it as a single large object value. The data is not sorted, so there is no efficient way to get to a particular row. ColumnStore indexes are intended to be used when you want most or all of the values in one or a subset of columns. The entire column, or at least entire segments, are read. There is a possibility of something called segment elimination if the data you're interested in is known to be completely outside of this segment, but because the data isn't sorted, that is not a very frequent occurrence. So let's look at a graphic which might make things a little bit clearer as far as how the data looks different, how the index looks different than a row store. In the example here, I have a table with 4 columns on the left. A, B, C, and D are my 4 columns. I built a column store index on A, B, and C. So D we're going to ignore. After I've told SQL Server I want the index on these 3 columns, SQL Server splits the rows into groups, and the maximum size, the preferred size we can think of, is about 1 million rows. It's not, I'm saying about because it actually is bigger than a million. It's the power of 2 that's just over a million. 2 to the 20th is 1,048,576, and that's the ideal number of rows in a row group, but not all of your row groups will be that big. So split your rows into row groups, and then for each column in each row group, take all the data, all million values there, encode them and compress them and crunch them together and come up with a single large object value as if it was an image value or a text value, and it's stored where SQL Server would store the text and image data for a table. Non-clustered column stores are the indexes that were introduced in SQL 2012, and one of the big restrictions on non-clustered column stores, which seems to have delayed their adoption, is that once you build a non-clustered column store, the table becomes read-only. Once you build a non-clustered column store, nobody can make any changes to the table itself. No inserts, no updates, no deletes. The only thing you can do is a partition switch to add a whole new partition's worth of data into the table if it's been partitioned. You can build other indexes on the table, however. You can build other Rowstore or B-tree indexes on the same table. Those will be useful if you want to look up individual values. It doesn't change the fact that the table is read-only, but it does give you the ability to have a where clause to find particular rows in the table that meet a certain condition. In the ColumnStore indexes, again, we can't find particular values very easily, and SQL Server has to read the entire column or at least entire segments of the column. So the picture here on this slide shows you sort of the same thing we just saw, a ColumnStore index with 3 row groups, and within this row group it looks like there are 6 different columns, so I have 6 segments per row group. But this is also illustrating what's different in 2014 if you build a clustered column store. Now, this took me a little while to really get comfortable with because I had been thinking of the definition of clustered from my B-tree indexes. The clustered indexes that I just told you about for the B-tree indexes have 2 specific properties different than non-clustered. The properties of clustered B-tree indexes are that the data is sorted and that the leaf level is the table. The index is the table and the data is sorted. Only one of those properties is true for a clustered column store index. There is no ordering. There is no sort order. There is no key column in a clustered column store index. The only property we have is that the index is the table. When you create a clustered column store index, SQL Server takes your data and converts it into this column store structure. No other indexes then can be built on top of it. It's the only index you can have, but the good news is you can make modifications. And this picture is indicating how those modifications can be made. When you want to do an insert into a table that now has a clustered column store, new rows are just added into a row store that looks like a regular heap from our row storage, basic storage. New rows are added into a row store, and only when we get to 1,000,000 rows there does SQL Server then convert it into a row group and take each column and compress it and encode it and store it as a lob value. But it waits until it gets 1,000,000 rows to do that, or 10 to the 20th rows. Inserts just add rows to one of these row stores. When you do a delete, all SQL Server does is mark the row as deleted. There is a bitmap, 1 bit per row. It might be lots and lots of bits, but that doesn't get really big really fast. And anytime there's a delete, the appropriate bit in the bitmap is set to 1. So when you do a select, SQL Server always has to check the bit in the bitmap to see, is this row really here or not? So inserts add new rows to the row store, deletes just mark the deleted row in the bitmap, updates, of course, are just both of the above. Updates will add the new version of the row to a heap in a row store and will mark the old row as deleted in the bitmap. So when can you consider using ColumnStore indexes? The main use for them, because of their inability to be updated easily and their inability to do seek operations, which means looking up one specific value or just a few specific values based on a where clause, the main purpose of them is for reporting kinds of queries where you want most or all of the rows in a column or a subset of columns. I want to see the sum of all of the quantities where product ID equals 47 or product type is like vegetables. So you're just referring to a subset of columns, but you want all of the rows because you're running some sort of report where you're looking at lots and lots and lots of data. Non-clustered column stores, of course, have the additional restriction that the data is read-only, which of course fits into reporting applications. Very frequently you have tables used for reporting that are not updated. The good news with the non-clustered indexes is that you can have additional B-tree indexes so that you can run seek operations, you can have where clauses and look for particular rows. The clustered indexes I did mention are updatable. Inserts, updates, and deletes are all possible. You can also do batch updates. You can also do a bulk insert into a table with a ColumnStore index on it. And then as you get, for each million rows, the row groups are then automatically converted, the heaps, separate rows of a million rows are automatically converted into the row groups as the load is taking place. For both clustered and non-clustered, actually, you can't define the ColumnStore index as a unique index. Uniqueness needs the capability of doing seeks in order to verify whether a value is already there or not, and there is no efficient way to guarantee uniqueness, so ColumnStore indexes do not support that property. And then the third flavor of indexes, introduced in SQL 2014, in-memory indexes. Now, in this section, this took me quite a bit of time to put together here because just talking about the in-memory indexes is not real easy without talking about the tables themselves. And I knew there wasn't time to talk about everything about the in-memory tables that might be interesting, but I'm going to do the best I can here. I will just give you a little bit of information about the new in-memory storage that is necessary in order to understand the in-memory indexes. And the reason I'm calling them NoStore here, besides the fact that I think it makes a cute title for the presentation here and it rhymes with Rowstore, is that the data is not normally read from disk. For both B-tree and ColumnStore indexes, the data is stored in our data files. Our MDF and NDF files is where the data originates, and only when you query the data does it get read into cache, into memory. For in-memory indexes and tables, all the data is in memory all the time. Nothing ever needs to be read from disk during query processing, so we don't have to store the data out to disk. It turns out there are two flavors of in-memory tables you can create, whether or not you want the data to be persisted. A persisted table will be written out to disk, but not as you make the changes, and certainly not as you query the data. It's not read in as you query the data. There's a background thread that will continuously be writing new rows out to disk only for recovery purposes. The only reason SQL Server needs the data stored on disk is in case of a crash or a shutdown of some sort. If SQL Server comes down, we of course lose everything that's in cache. When SQL Server starts up again, if we want to be able to get the data from these in-memory tables and indexes back again, we need to have it in a non-volatile storage. So we've got it out there, but it's not used during normal processing. I'm not going to say much more about how the data is stored on disk. That's a big topic in itself. I do want to mention, though, that the in-memory tables are in memory all the time. And so in just a minute, we will talk about the indexes on these in-memory tables. I do have a slide to give you a little bit more background about why the in-memory OLTP is such a powerful technology. You might have heard the code name. In fact, in the book I wrote about it, I did use the code name. It's called Hekaton, and a lot of people still refer to this technology as Hekaton. Hekaton comes from the Greek word 100, for 100, and the vision is that eventually this technology will allow you to improve query performance 100-fold, not 100%, 100-fold. And there are already applications using in-memory OLTP that are getting 30 to 40 times performance improvement, and nobody who's using this extensively, none of the engineers at Microsoft have any doubt that they will eventually get to that 100 times better performance. So there are 4 components to the, an in-memory database, or the technology that allows this in-memory storage. The first is completely redesigned table and index structures, and that's what I'll be telling you about shortly over the next couple of slides. The table structures have been, and the row structures have been completely redefined, and the index structures are completely different than what we've just looked at for Rowstore and ColumnStore. Writing the data out to disk is done with a stream-based mechanism, as opposed to just writing out changed pages. The second aspect of in-memory OLTP that allows some incredible performance improvements is that your stored procedures can actually be truly compiled down to machine code. We're not going to be going into details about that in this session. The data structures developed to store your tables and indexes are completely latch and lock free. If you've ever experienced slowdowns only because of concurrency issues and multiple users competing for the same data, you'll appreciate just how much improvement you can get when you completely eliminate locks. And latches are like locks, but they're on the internal structures. Those are not needed also because of the new storage mechanisms. And what I find is the best thing about in-memory OLTP is that it's fully integrated into SQL Server. When you install SQL Server 2014, it doesn't even ask, do you want to install in-memory OLTP or not? You just get it. You don't have to use it, and then there's no cost associated with it. But as soon as you install SQL Server 2014, you can start building, creating, and testing some in-memory tables, and you can use your normal tools, SQL Server Management Studio, SMO, and PowerShell, and there are also several dozen dynamic management objects for giving you information about your in-memory tables and indexes. So, because the focus of this session is indexes, I want to make sure that I tell you the key features about indexes on in-memory tables. The truth is, indexes are really all we have for an in-memory table. There are no in-memory tables. There are in-memory rows, and these rows are just floating around in memory wherever there happens to be room for them. What connects the rows together, the way SQL Server knows that these rows belong to the same table, is your indexes. You must have at least one index on every in-memory table. In fact, it is required in the syntax that you have a primary key declared, and that could be your only index. You can, of course, create other indexes. There is a small upper limit. You cannot have more than 8 indexes, but that might seem like a small number, except if you think about the fact that these tables are intended for OLTP kinds of operations, and very frequently for OLTP operations with heavy inserts, updates, and possibly deletes, it's always recommended that you keep your number of indexes to a minimum. And usually, I recommend that you not have more than 5 or 6 indexes on a heavily updated table. So in-memory tables allowing up to 8 usually is sufficient. The 2 flavors of indexes we have are called hash indexes and range indexes. Now, range, notice I put in quotes. I do want to stress it is not part of the syntax. The syntax just says non-clustered. For the first kind of index, you'd say non-clustered hash. And to me, that sounds a little bit funny that one is just called non-clustered and one's called non-clustered hash. So if somebody says non-clustered, I'm not sure if they just haven't mentioned the word hash yet. So I like to always add, I like to make the terms orthogonal so that I can easily compare them. Non-clustered hash and non-clustered range is the way I refer to them, or just hash and range. Hash indexes are very useful if you are doing single value lookups. We call those point lookups. Select from table where country equals Zimbabwe. Select from table where first name equals Joe. Select from table where last order date equals January 1st, 2015, where we're looking for a specific value, and the hash index can find all the rows with that specific value very easily. You do need to define a number of hash buckets as part of the index creation. The hash buckets are all the space the index needs, so it will be fixed. You declare the index with a fixed number of buckets. That number is not changeable, but you know right up front how much space the index is going to require. Range indexes use a tree structure, which looks very similar to the B trees I just showed you. They're slightly different, however. We're not going to be able to go into the differences in this short session, but the name of this kind of tree has been given as, or the Microsoft developers came up with the name BW tree for this particular variation of a B tree. These range indexes, or these BW tree indexes, are good for searches where you need ordering to the data, either where you need to select all the rows in a particular order, or when having the data near other values in a range is required. Select from the table where date between January 1st and February 1st. A range index on order date, all those rows would be stored near each other, would be easy to get to as that range. Now, a fact about the indexes on your memory optimized tables is that the indexes only exist in memory. There is nothing about the index structures that is written out to disk. What gets saved on disk is the rows themselves and indications that of which rows have been deleted. We have the inserted rows and we have the deleted rows. We do not have any index information on disk. We do not log any changes to indexes. When a database has to be recovered, all of your memory optimized rows are read back in, and the indexes are built on the fly as you're doing the recovery. The indexes only exist while the tables are in memory. So if you did download the slides before the session, you might notice that this particular slide is new. As I was going through this right before my session started, I realized I didn't have any diagrams for memory optimized indexes, so I thought I would put one in for hash indexes. And if you've never even thought about this kind of storage before, I know I'm not going to be able to explain everything in just a couple of minutes here, but I want to at least give you something to visualize. This is an example of a table that has 2 hash indexes on it. A hash index on name the buckets are shown on the left and a hash index on city. The buckets are on the right. The rows have some timestamps in them that we're not going to be talking about now. They also have a set of pointers because it's the pointers that connect the rows together. In the picture here, I've got 2 rows for the same city. I've got 2 rows for Prague. So Jane in Prague and Manuel in Prague, those rows are linked together. You can see that red connector going from the Jane row to the Manuel row. If there was another row in Prague, there would be a pointer from the Manuel row to the next row. All the rows with the same value for city are linked together. All the rows with the same value for name are linked together. So if we said, select from this table where name equals Susan, SQL Server would take that value Susan and crunch it through its hash formula and figure out which of the buckets to look in. And in this picture here, it looks like Susan would lead it to the 4th bucket. And so from the 4th bucket, it would follow the pointer to that row for Susan in Bogota. If there were other Susan rows, the first Susan would point to the next Susan, which would point to the next Susan. So the rows only exist once. I have 3 rows in the table that are shown here, and we have 2 different indexes which point to the rows and connect them in different ways. If we had a range index, there would be pointers from the leaf level of the range index to these same rows, which then would also link together duplicates. So I know this is fast and furious and not really enough information to understand everything, but the main thing I wanted to show you here was just how different these indexes were than the Rowstore and ColumnStore that I previously mentioned. So when should you use in-memory indexes? Well, certainly only on in-memory tables. In-memory indexes are the only indexes that you can have on your memory optimized tables. You do usually need lots of memory. But if you've got lots of memory and you have a need to greatly speed up your operations, either just because you've got such a high volume or because you've got blocking which you haven't been able to overcome in any other way, you can think about in-memory indexes. And another one of my favorite features about this technology is you don't have to, it's not an all or nothing choice. You can take one table and convert it to an in-memory table and run with that for a while and then convert another table and go with that for a while. Or testing, you just need to do one table at a time. Your hash indexes are useful when you're doing point lookups, which again means looking for an equality in a where. Select rows where name equals Susan. Select where city equals Prague. If you have a composite index, you do need to be aware that all of the columns in the index must be specified in the where clause in order for a hash index to be useful. Your range indexes are useful if you don't meet the conditions for hash index. If you're looking for a range of data as opposed to a point lookup, or if you're looking for only a partial match for a composite set of index keys, a hash wouldn't help, so range would be the only option there. So for the next couple of minutes, just to finish up here, I want to also do some comparisons between the 3 types of indexes for the aspects of indexes we usually need to pay attention to. How does fragmentation issues, how do fragmentation issues vary for the 3 kinds? What's up with statistics for the 3 kinds of indexes? And what kinds of maintenance operations are possible? And these slides I'll go through relatively quickly here, so we'll have time for a few questions. B-tree indexes are the main ones that we need to be concerned about fragmentation. But I just want to give you my bottom line about fragmentation, and that is fragmentation doesn't always hurt you. You need to know that there are certain queries where fragmented data is not going to perform any worse than unfragmented data. So if you've got a regular schedule of removing fragmentation on every single table as soon as it starts to display any fragmentation, you might want to rethink that. If you verified that removing fragmentation will actually improve performance, then by all means, schedule regular operations to remove it. This could be either rebuilding or reorganizing the index. Keep in mind that if you do a rebuild, SQL Server will also update the statistics, which we'll talk about on the next slide. ColumnStore indexes really don't have a concept of fragmentation because fragmentation really has to do with the order of the data. Fragmented data means that the logical and the physical order don't match. We have an index on name, but our A's are in one place and our B's are at the other side of the file, and our D's are in the middle and our E's are somewhere else completely. The data order A, B, C, D doesn't match where the data is physically stored. Logical and physical order don't match. It's fragmented. In ColumnStore indexes, because there is no ordering, fragmentation really doesn't mean anything. There is an operation we can do on our ColumnStore indexes, though, called reorganize, the same reorganize we do for our Rowstore indexes. If we say reorganize, what it does is just, no matter how many rows are in these delta stores, these extra row stores for the new rows, it will convert them into the ColumnStore special storage. Even if there were only 10 rows there, it would build a column store with those 10 rows. So obviously this is only for your clustered column store. These are the only ones that can have these extra rows for new inserts. If you do that too often, you can end up wasting space, and you might think of that as a flavor of fragmentation, but it's not the same as the B-tree fragmentation at all. And for in-memory indexes, fragmentation again is meaningless because we don't have data read from disk. It's only when we read data from disk that data not being near other similar data can be an issue. So external fragmentation is meaningless. In the BW tree indexes, there could be wasted space on the pages, but that is rarely going to cause performance issues. If we do have large delta files, which are the files which keep track of the rows that are deleted, we could think of that as a kind of fragmentation, but it's not really in an index, so it's out of scope for this talk. Statistics are another issue that's of great concern to index management, but it's mainly a consideration for B-tree indexes because here you've got a choice about how often the statistics are being updated. There is a semi-undocumented trace flag, 2371, which changes the frequency that statistics are updated. I say semi-undocumented. It's not in the books online, but it has been written up in several articles by Microsoft engineers, so it's like known and available. You can do an online search and find information about using that trace flag, or you can come to my full day session and I'll talk about it some more. ColumnStore indexes don't use the irregular distribution statistics. The only statistics type information that's available is the minimum and maximum value for each segment, but there's no way to update that other than dropping and rebuilding the whole index. In memory, tables do have statistics kept, but there is no automatic update of the statistics. You do need to do a manual update of those statistics. And if you have natively compiled procs, those will never be recompiled automatically. Those you need to drop and recreate if you want them to take advantage of new statistics. And then the last technical slide here is maintenance operations for our Rowstore B trees. We can do a reorganize or a rebuild. Both of those can be useful to take care of fragmentation issues and a few other issues as well, such as forwarding pointers. ColumnStore indexes, if they're clustered, we can do a reorganize, which will just cause all these extra rows to become actual row stores. Or if we do a rebuild of a column store, that is something to consider when you get too many deleted rows. It becomes inefficient when half your rows have been deleted and all the rows are still being stored. So at that point, you might want to do a rebuild. In-memory indexes, there is no maintenance possible. No alter indexes are allowed for rebuild, for adding new columns, or even for dropping indexes after a table has been built in SQL Server 2014. So I wanted to give you a comparison here. I wanted you to get a flavor for what the 3 different kinds of indexes look like and some idea for how they might be useful. In my full session, I will go into a lot more details, and I'll say a few things about that if we have time after any questions. Howard, what's come up for us?
Thanks, Kalen. Thank you for that. I think there are several questions relating to what's new in SQL 2016. So I wonder if you could, if you wouldn't mind answering those.
Okay, are they specific questions and not just what's new?
So I've got what's new in SQL 2016, and then I've got, do you have any information about the differences between clustered and non-clustered ColumnStore indexes upon in-memory tables in upcoming SQL 2016?
Okay. Yes, I do have some information, but it would take too long to talk about ColumnStore on in-memory, but I'll just tell you that we can have ColumnStore indexes on in-memory tables in 2016. But at this point, I'm not going to be able to say any more about that. I am updating the white paper that I wrote on memory-optimized tables for 2016, and so I will include information on the ColumnStore indexes in that. What is new, I will tell you that this last thing I just mentioned about not being able to make any changes to your indexes, that has been loosened up quite a bit. In 2016, you can change the bucket count for existing indexes. You can add a new index, you can drop an index, and the tables themselves can also be altered. You can add and drop columns. I know people have been waiting for those features, but let me just give you a caveat about them. Yes, those features are allowed, but they have not been implemented efficiently. Microsoft decided it's better to give it to you, and you decide whether you want to use it or not. In 2016, when you add or drop an index, the entire table is rebuilt, and every row is logged as that rebuild is going on. So it can be quite an expensive operation, but at least we do have the option of making those changes.
Thank you. So, we've just run out of time there, if I can just wrap up. Thanks a lot, Kalen. If we could go to the next slide. Like what you've heard, Kalen will be presenting at the PASS Summit 2015, pre-conference sessions, index internals, Rowstore, ColumnStore, and NoStore, and a general session of how minimal is minimal logging. Use the discount code 24HOP15 to save $200. And you can stay in touch at SQL Queen on Twitter and SQL blog. Next slide. Thank you for attending the highlights from Index Internal, Rowstore, ColumnStore, and NoStore. I'd like to thank Kalen Delaney for her time and her expertise. Again, I'd like to also thank our presenting sponsors, Microsoft, Idera, and Dell Software, and our supporting sponsors, Pyramid Analytics, SQL Sentry, and HP. We hope you enjoyed the session as much as we did. Follow along on social media with @PASS24HOP and share your thoughts on the event with hashtags PASS24HOP and SQL PASS. Next slide. Stay tuned for our next session, Taking the Scare Out of Monster Reports with Pam Shaw, happening in a few minutes. Thank you very much.
Thank you, Howard, and thanks everybody for being here.